I'm involved in luminescence chronology, trying to apply it for different paleoclimatic studies, earth surface processes, and for the archaeology. So from here, like, first of all, why we want to study, like, even the geological process or the archaeological process. For the geological process, I can say, like, we have to build a story. We have to see how the a particular landform has evolved in the past, and since we want to understand the evolution of a landform, or say the paleoclimate in the past, we should understand the timeline, how this time has progressed in the past. Similarly, for the archaeological purpose, we know that somewhere, like, down in the very beginning, human originated in Africa and then expanded expanded throughout the world, and moved throughout the world. The question is, what are the stages at which the human migration happened, and actually what are the types of the tool technology, what type of people are making which type of tools, how this evolution happened, when it came, our perspective, when it came to India, and how the Indian climate influenced this evolution. So all these studies, the behavioral changes, the existence, and the timings are the important aspect. And timing is an important aspect because these times are, we know a particular climate change occurred at a particular time, and how that climate is influencing the evolution of the things, evolution of the human. That is an important aspect. So unless we fix the time, we will not be able to means constrain or draw a conclusive line how this whole evolution or the migration happened. Similarly, we have several settlements, even in India and other parts of the world, like Lothal, Mohenjo-daro, or Harappa settlements. All the Harappa potteries and these kind of things are there. The question, although we at present day we only see the ruins there, whatever those early people have made, we see those their structures, we see their potteries, these kind of stuffs we find. The question is, when this cultural settlement has begun, when it was at its full flow, when it was fully grooming, when it came to end, and why it came to end. So all these questions arises. Obviously, at a particular time, some event might have happened that led to the decline of these civilizations. But what is that time, and whether this time can be correlated to some natural calamity or some other things? So those aspects are the second aspects we have to look into. But unless we set the timings of these things, we will not be able to draw a conclusive timeline or the sequence of the event which has happened during the evolution, or during the, like, from the beginning to the end of these particular civilizations. So just to give you the glimpse, the first thing, when you go for you are geologist or the archaeologist, when you go to the field excavations or you go to a field sections, the first thing which you observe is a geological or archaeological section. So in this geological or archaeological section, what you observe? You cut the section and you observe different kinds of layers. You observe, like, the topmost layer is always most of the time humus layers, and then following layers of the different colors and different thicknesses. So what is the meaning of each layer? Obviously, you are taking up the lectures in paleoclimate and geology in past lectures. They must have talked about these layers, why such things are happening, why some layers are big, why there is a difference in the color. Basically, each layer tell about its deposition time. When this layer is depositing, how the climate was at that time. What is the nature of deposition, whether it's a fluvial deposit or a aeolian deposit, what type of environment, whether it's a humid environment or a dry environment, like the colors. And if you further go into the details, if you do the oxygen isotope studies or stable isotope studies, you will be able to know what type of climate was present in these layers. And another interesting feature which we observe in these layers are some important species things, like from the top layer. If you go in the top layer, which we also say present day layer, sometimes you find some tools on the top, potteries on the top, some carbon charcoal on the top, or some coins. Similarly, in the second layer, you may find potteries, coins, and shells, these kind of stuffs. So these kind of stuffs tell you the depositional environment, at what time, what is happening in these layers. Some layers, sometimes you find these layers as a thin deposit, all the potteries in the same section. And obviously, since potteries are in last 300 4,000 years only, so they are mostly found in the top layer. On the other hand, the archaeological tools, since they are older, they are found in the deeper layers. Other features you observe, like in sometimes you may find some eggshells, or sometimes like boulders in the. So these are the materials which are associated with these layers. So the question is, can we, because each material has a story to tell, you have to probe that story, and it will tell what processes it has gone through. So if we analyze all these materials, it has some tale to tell about itself. So we will discuss that in the later part of my slides. And right now I concentrate on the chronology. So the question is how the timeline goes in this. Obviously, the time progresses as this, because top one is the present day layer, and as we dig and go deeper into the layer, we go back in the time. So as we dig deeper, we progress deeper into the time. So as a function of time, or as a function of depth, we will be able to predict the climatic changes, or the landform changes, or the human occupational changes, or other related activity. So basically, we have to go to section, collect the sample. I will discuss about how the sample is collected and this thing. So the most important thing is, since this axis from top to bottom represent the time, first thing I should know how to estimate this time. And what are the materials we can date which can give us time. And another important aspect, what are the techniques available which can be used for date. Okay, so you can see there are various dating techniques which are extended up to different time ranges, like dendrochronology, radiocarbon dating, potassium argon, lead-210, fission track, luminescence, ESR, and amino acid obsidian hybridization, archaeometry. And these are the techniques which are really being used for estimating the ages. And you can see one of the important technique in this category is luminescence dating. Another important, lead-210 and uranium dating also, because it is covering almost an entire range. And most important for the luminescence is, for other techniques, it may be possible that material which is required to date is not present. But in case of luminescence, we work on sand. So you all know that sand exists everywhere. Almost, we mainly work with two minerals which are present in the sand, which are quartz and feldspar. So these minerals are present everywhere almost in the nature. Okay, so basically we say it is, since it is based on ubiquitous materials, we can apply it anywhere. Anywhere means there are some restrictions which as I go through the slides, I will let you know what are the ideal conditions for application. Okay, so since these are applicable on quartz and feldspar, which are ubiquitously distributed, we can use for a wide range of studies, for obviously dating only, and also nowadays we are applying it for provenance studies and for exposure dating studies also. So it has nowadays it has gained quite a lot of attention, and from a very like humble beginning in somewhere 1960s, now it has groomed, and again there is still being progress where I have indicated in these time ranges people are working continuously to extend these time ranges. And to cover this, there is no other technique which can cover this entire time range. So it's an important technique to understand. So question is, what is the luminescence dating? Okay. Now we mean luminescence and dating. Okay. So it is basically made up of two parts, luminescence and dating. So let's try to understand each part separately. First we understand what is the luminescence. Second, we try to understand what is the dating. Okay. So let's try to understand luminescence. So first thing which we say that luminescence, everybody can make out. Okay, luminescence means light. The question is, can any type of light we call luminescence? Like we are getting light from the candle, or when we do burning a fire wood, then also we are getting light. Light bulb also, from sun also we are getting light. Torch also we are getting light. Can we say these sources of light as luminescence? I think we, in your daily life, you would have never used the term luminescence instead of light for these these kind of lights emitted from these bodies. Basically, this is the light which is emitted from the hot sources. So, on the other hand, we say luminescence, or we use term luminescence for the light sources which are emitting light while they are cold. So we are also called it a cold light. So you must have seen the jugnu, we call it like glowworm. Okay, so it emits light in the night, but it is not burning. It's chemical reaction or biochemical reaction which is giving rise to light. So we call it luminescence. Similarly, LED light, or sometimes nowadays you use glow in dark material or glow in dark clothes. So these are also called luminescence. And also on the beach side, sometimes when you go on the light, you see some light is emitted. So all these stuffs which are emitting light while they are cold is called luminescence. So now question is dating. As Prath said, dating could be this, but obviously we are not talking about this dating, we are talking about this dating. We are talking about dating earth, minerals, and the nuclear things, nucleus related or atom related things. So what is the actual meaning of dating? Dating, as far as we understand, dating means time. When a reset button is pressed and when the clock is started again, so it starts from a reset point, and the time elapsed, we take a note, and that is called the time. So we can call this as in terms of geology, we call it as a date, that a clock is reset, and after some when we start the start button, it starts counting. You sometimes like from the face of a person, you can predict what is the age of a person. If you see the body and other things of a person, you can say how old he will be. He will be 5-year-old, or he will be 20-year-old, or he will be 60 or 40 years old. So what are the things you are observing? That means something you are observing which is changing with time, and based on your current understanding, you know at a particular time a person should look like this. That's why you are saying that this person is this much old. So you have a reference point for that. So that means some expression, something should change with time. Some physical parameter should change with time if we want to date something. Now comes then how the luminescence is related to time, or date is related to the age, obviously. So how we can correlate the luminescence with the time? Let's try to understand that. How I am saying luminescence is a cold light, but then how cold light can be related to the time? Okay, let's go for it. Everybody must have seen the two kind of things. One is the fluorescent marker they are using in their office. Another thing is a material which we used to call radium when we were young. That now what you do, you show a light, say blue light, to the fluorescent marker. You will see why we call this fluorescent. Sometime you go to your home, just mark something with a fluorescent marker and show a blue light with or under the blue LED or blue torch or ultraviolet torch, show it this marker. Then immediately switch off the torch. You will see that as soon as the torch is on, the whatever is written with the fluorescent marker, it becomes so shiny, bright, it shines like a silver. If you just try to do this experiment in your home, and as soon as you switches off the torch, it stops shining immediately. On the other hand, in this kind of material which we are calling radium, although this is not a radium, this is a misnomer, we say it phosphorescent material basically. We will see that as soon as you switch off the light, when the light was on, it was glowing very brightly. However, when you switch off the blue light, it still glows in the dark. It emits light for some time, even if normal light is not present. That means it has some property that it is storing the light of the blue light which you are giving. In this case, it is not storing the light. In this case, it is storing the light. So if we can store the light for, say, sufficiently geological time scale and then measure that light afterwards, can we estimate the time when this was the time of its exposure, for how long this is exposed to the blue light? So this is all we are going to discuss now. Hope the point is clear up to this. If you have any if you have any question, you can raise that immediately. So next, as I said, it's not a radium. It was because in the earlier time people used to mix radium with the phosphorescent material, which later they came to know, okay, this is a radioactive, this is a harmful material. So they stopped mixing that material, but name continues still. We still call it radium. So now the question comes is, as I said, how the luminescence is occurring, how it can be used for dating, and how these kind of materials are actually storing the light in them. Okay, so this is a small physics part of it. I will try to make as simple as possible. If not clear, please let me know. Okay, we know we have crystals, like I said, quartz is there, feldspar is there. So we have a crystal. In normally perfect crystal should not have any defects. However, the natural crystal always have some defects. Some kind of defect, either something is present in between, or some atom is missing, or some other type of substitutional impurity is present. So what this will do? Normally, in a perfect crystal, it is only conduction band and valence band. But if impurities are present, some metastable states, we say, some allowed states are formed within the forbidden band. And when such a crystal is ionized by the ionizing radiation, say alpha, beta, gamma. Now in the soil, we have uranium, thorium, potassium, which are continuously emitting these radiation, alpha, beta, gamma radiation. So what will happen? This will ionize the crystal, create electron and hole pair. Now, what these impurities are? These impurities are electron deficient, so they will attract the electron. And what will happen? So most of the electron will recombine immediately, they will give fluorescence. However, a small portion of the electron and hole will get trapped in these impurity sites. Okay. And as the irradiation continues, if this irradiation continues with time, the concentration of trapped electron and hole goes on increasing. Now, important point to note is the lifetime of these trap is varies from few seconds to billion of years. What it means is that it can store, some of the traps can store electron for billion of years. That means they will not lose electron with time. In fact, if irradiation continues, their concentration goes on increasing. So they are stable in time. Okay. Now, what happens when we heat such a crystal, either by heat or by the light, or stimulate these crystal by heat or light, electron gains energy. They goes to conduction band and recombine with the hole, and they give light. This light is called luminescence. Now, since it is from the cold source, we called it a luminescence light. So that's why. So this is how the light is being stored. Light is being stored in form of the electrons, or energy of alpha beta is stored in form of the electrons in the crystal. Now, when this crystal is stimulated, given some heat or given some energy in form of heat or light, these electron comes out and recombine to give luminescence. Important point is, now we see this luminescence is proportional to trapped electron. More the trapped electron, more will be the luminescence. And this trapped electron is proportional to the dose. Dose means energy per unit mass. So luminescence is proportional to dose received by the crystal from these alpha, beta, gamma radiations. So if we can measure this luminescence, we can measure the dose. And if the rate of energy deposition is constant, we can estimate the time. Okay. So this is the simple principle on which luminescence works. That luminescence is proportional to the trapped electron, and it is proportional to the energy received by the crystal from the alpha, beta, gamma radiation. And when we, at a constant rate, this energy is deposited, we can link the luminescence with the time straight away. What do I mean by that, and how do we do it? Let me show you. Suppose I start heating the crystal at a constant heating rate, say 2 degrees Celsius per second. So what will happen? The traps which are shallower or require less amount of energy, they will release their electron first, and we get a luminescence signal from there. Again, if I keep on increasing the heat or temperature, another set of traps will release the electron and start giving the light. So this is what is happening. If I am increasing the light slowly, one set of trap is releasing the energy, so I am getting a peak. Again, when I further increase the temperature, this is the shift, is the change of the scale, nothing more. So if there is a further increase in the temperature, we get signal from different release of different electrons. Now these traps are stable in time with different stabilities. Like generally the high temperature traps are the ones which have a lifetime of billion of years and used for thermoluminescence dating or TL dating, which we say. Similarly, if we stimulate them with the light, so now light is always having a fixed energy, lambda is equal to energy is equal to h nu. So if it's a blue light, all the electrons which are having less energy, which require energy less than the h nu energy, they will come out, and slowly their concentration starts decreasing. So what we get the signal which is decaying with time. So initially the signal is higher because all the electrons are emitted at once, and slowly their concentration decreases. So we get the OSL decay curve, or this is optically stimulated luminescence. In generally for the quartz we use blue, stimulation for feldspar. In case of feldspar, we can do the IR stimulation also. If somebody is interested, I will tell the reason with the IR stimulation. Now, let's again come back to the luminescence dating. So, what is happening to the luminescence signal in nature? In nature, suppose you have a new crystal is formed, magma cooled. So magma is cooled, a new crystal is formed. What is happening there? Now crystal is heated to, if the magma temperature is normally very high and crystal is heated to very high temperature. So there is no electron capture trapped in the trapping center. So, but due to the, when the magma cooled down and it is shielded from light, slowly the ambient radioactivity, uranium, thorium present in the surrounding sediment, they starts depositing uranium, alpha, beta, gamma radiation. As a result, its luminescence signal starts increasing. Now, after some time, suppose the rock withers away and the sediment starts is blown in the nature, okay, or some the like clay mineral is there, some clay is collected by some potter and he heated the sample and make it into a pottery. So what will happen? Its luminescence signal was increasing, but as soon as it sees the sunlight or the heat, again its signal comes down to the zero level. Again, this pottery or this sediment get buried. Again, due to ambient radioactivity, its luminescence signal will start increasing. Now, at some point of time, we go to the section and we excavate that mineral out of it. Either we collect the potteries or the sediment sample. So, at this point, we can tell the date when the signal is last reset. If we collect sample somewhere here, we will get the crystallization age. However, if we collect sample somewhere on this line, we get the last resetting, either the transport time or the heating time when the sample was, after which the sample was buried in the soil. So basically using luminescence, we can date a crystallization event, we can date a burial event, and excavation, and after excavation and analysis, we can estimate these kind of ages. So we can date the crystallization, thermal event, or the last light exposure event. Okay. So let's move on to, let's try to understand the basic of dating. Okay. Consider a beaker. Okay. It is filled with some water, and we know that the water is being filled in this beaker at a constant rate, some volume rate. So how can we estimate the time? Time is simply the total volume in this beaker and the rate at which this volume is filling. So we can estimate the time simply dividing volume by the volume rate. However, there can be some complications in it. Suppose right now we are considering that at t equal to 0, beaker was empty. But what will happen if beaker is not empty? There is some water already present. Then our volume will be different. And whatever time we will estimate, that will be an overestimation. That will be slightly higher than the actual time because of the presence of some initial volume in this mineral, beaker. Or if the beaker is leaky, we are also losing some water. So this is some complication. We have to know at what rate it is leaking. Sometimes it may happen. Someone might have added something. That also creates a problem. Or the rate, the volume rate is not constant. It slightly changes in between. Then also we get wrong estimation of the ages. Or if whatever method of measurement we are using, they are not correct. If they are not correct, we will not be able to measure the correct volume or correct volume rate. In that case also, our time can be different than at the actual time. So we have to take precaution in these terms. I will come back to this slide after we discuss in terms of the luminescence now. Okay, so luminescence is basically a correspondence of this. Okay, so in this case, you can consider water as a dose and volume rate as a dose rate at which the dose is deposited. So basically, in luminescence dating, we estimate the age in a similar way: dose acquired by the crystal and the rate at which dose is deposited. Now it has two parts. One is dose acquired, how so we have to estimate the dose acquired by the crystal. We have to estimate the rate at which dose is acquired. To estimate the dose acquired, the method is very simple. Suppose now we collect the sample from the field. Okay, we bring the sample from the field. We do some chemistry and separate the mineral of our requirement. As I said, quartz and feldspar. So we separate quartz or feldspar from the sediment sample. Okay. Now what will happen? We measure the initial luminescent TL or OSL signal of this sample. We see it has some sample which is lying somewhere here. Okay, very good. Now, since we measured this signal, so that means our traps are empty now. Since we have either heated the sample or given light, so all our traps are empty. The signal is zero. So my signal reduced to zero. Now in the lab, what we will do, we give a known beta dose. Since we are giving a known beta radiations, some signal is generated in that portion, and we measure that luminescence signal and plot it. Similarly, we give another beta dose, beta 2, and measure the luminescence signal corresponding to beta 2 dose. And similarly, we do give another dose, beta 3, okay, and measure the another luminescence signal, and plot it. So we see we can draw a calibration plot that if we give this much beta, we get this much luminescence. This much beta, this much luminescence. This much beta, we get this much luminescence. So we plot a calibration curve and interpolate the initial natural signal on this calibration plot, and we will be able to estimate the dose acquired by the crystal. Okay, so this is the simple way we can measure the dose acquired. Another important aspect is the dose rate. Dose rate is basically because of, as I already said, is because of the uranium, thorium, potassium, and the cosmic rays. I will come to this part after some time, okay, slowly as I progress. Now, you know how the dose is acquired, but this is a very simple procedure I am explaining here to you. In the laboratory, actually, we do a cumbersome process which takes some time, and we have to do some normalization stuff. And this is the actual protocol which normally we use in the lab. We have a regenerative protocol SAR. Another protocol is multiple aliquot additive. We use these type of protocols for measurement of the dose in the laboratory. I will not go into the details because it may be confusing to some of you. But if someone needs to know, please let me know later. Okay. So this is the simple way we try to determine the dose. Now, as I said, to measure the dose rate, we have uranium, thorium, and potassium, and some minor contributors, rubidium and strontium, rubidium, and uranium-235 is there, which contribute to these dose rates. We know it's a complete series in which several alphas and several betas are emitted by these series. So what we do is we measure the concentration of uranium, thorium, potassium. Now, since we know the concentration of uranium, thorium, potassium, we can measure in 1 year how many atoms are decaying. When one atom decays, we know how many alpha particle, beta particle, gamma particles are released and how much energy is deposited annually. So if we know the concentration of these elements and using this decay law, we can estimate the rate at which they are decaying, and hence we can estimate the total energy deposited by them annually. So we do this way and we estimate the rate at which energy is deposited. But in a year, how much energy is deposited by these uranium, thorium, potassium radioactive elements present in the soil after measuring their concentration. But the life is not so simple. the range of alpha, if suppose I have a 1 centimeter grain, okay, a pebble is there, then alpha is only in the exterior part. Beta is range is 3 millimeters, so it goes to the can deposit energy in the 3 millimeter portion, while gamma goes throughout the matrix or throughout the one. So gamma deposit energy throughout the crystal. So when processing the sample in the laboratory, we have to take these range factors into account. Also, this is important if we are going to the field and collecting the samples. I will come to that point also, okay, slowly, shortly. So in the laboratory, we have basically two types of techniques. We say coarse grain technique, which is basically the grains around 100 micron range, and the fine grain technique. Fine grain technique is when the grain size is around 4 to 11 micron. Now for 90 micron grain, what will happen? Alpha range is only 20 micron. So alpha is stopped in the skin. However, beta will completely pass through since its range is 3 millimeter. Gamma will also completely pass through. So both beta and gamma will deposit the dose entirely. Alpha is only in the skin, so we have to remove the skin. So what we do for the coarse grain dating, we remove the skin and we estimate beta, gamma and the cosmic ray dose rate only in case of the coarse. On the other hand, in 4 to 11 micron, all alpha, beta and gamma are depositing the dose. So we consider the dose rate, like in case gamma 4 to 11, like fine grain dating is basically used for pottery. So for these, we have to consider all the factors, dose rate factors, alpha dose, beta dose, and gamma dose rates. Okay, so these are the these are the things which make the technique a bit cumbersome to apply, as we have to do some extra experiment to use this technique. Okay. Now, as I said, we have to measure the dose. We have to measure the dose rate. So in case of like in PRL, there are several instruments which are used. We have the like TLOSL reader. So in this TLOSL reader, we have a like, you can see a disc is there, a platter is there. On this platter, we put the sample in form of a disc on the top of a stainless steel disc. This can rotate, and below it is a heater plate, and the optical source is above. So we can stimulate with light. You can see some light is coming also here. So we can stimulate it with light. We can measure the signal with PMT, and we have an inbuilt irradiation source which is marked as 4 here. So within the same system, we can do all the measurement automatically. The system keeps running for a longer time, but we will be able to say after 2 or 3 days, we will be able to estimate accurate dose for one sample. Okay, so this is normally the time it takes. We have several facilities. I will not go into the detail. We can go up to single grain laser level. We have a single grain laser system, which means we can measure a 90 to 100 micron grain. We can estimate the age of a single 100 micron grain here. We have radioluminescence, pulse stimulation, time resolved facilities which are being used. These are some advanced techniques which are applied for dating, not normally discussed as usual normally. Another one is the violet stimulation, IR stimulation, and automated filter changing assembly. We are developing some new protocols, and we have developed already some new protocols in which these violet and automated filter changing assembly is used. But normally in other system, in other labs, they typically use the normal IR, normal laser systems on normal light systems only, and they can do the work. These are some advanced systems which we are having here. Okay. We have a new alpha beta counter, which the name is MUDOS. We can estimate the concentration of uranium, thorium, and potassium, all the 3 elements in this particular system. We have alpha counters also. In the alpha counters, we can measure the concentration of uranium and thorium. We have scintillation detector, which are generally used for estimating the concentration of potassium. Then we have external beta irradiator, where we can irradiate the sample with the dose. Although we have in machine also, but sometimes if the irradiation time is very long, we can irradiate them outside. We have a high purity germanium detector, which is like high accuracy and high precision detector. It can measure the like concentration up to ppm level with less than 1% error in those measurements, with 1% accuracy level. And we also have magnetic separator. These magnetic separators separate the, like quartz is mostly diamagnetic, feldspar has some iron impurities in it, which makes it slightly paramagnetic. So we can separate quartz and feldspar also in this magnetic separator. So these are the facilities which are normally used for estimation of the, like this one is used for estimation of the dose. These are the facilities, alpha, this mu dose, spg and alpha counter are used for estimation of the dose rate or the concentration of radioactivity. So once we know it, we can estimate the age of the sample. Now, after this brief introduction to luminescence, let's go and try to see how we can apply the things in the field. When you go to the field, as I already showed you this slide, I said I will come back to this slide later. Now there are some important features to observe. Okay, we have some scripts tablets, we have some archaeological tools, or the pottery, or the like this charcoals, again some paleolithic tools or some coins on the top surface, on the top humus layer only. So normally if you collect such samples which are scattered on the top, on the surface, we normally avoid dating the surface samples. The reason is this sample has no context. It must be a part of some layer which was there, but since the layer or the sediment eroded away, different layers of different ages are coming together. And obviously they can be modern also, means some present day humans, they may have dropped it somewhere from after bringing it. So these kind of things have no context, so we normally avoid using the surface collected samples. So please be aware, because several people come to me and they say, sir, I have several tools and the potteries or several samples on the top layers, can we date it? No, we cannot date it. Okay, so always the whatever material, datable material you are getting, that should be coming from the section. Another thing is, what are the things in this slide which we can date? So we have several things, like we have a pottery. First thing is the sediment. We can date sediment itself. We can date the potteries, since this pottery and this sediment are in the same layer, so we can say they are contemporary, means they are deposited at the same time. So whether we date pottery or we date sediment, we should get the same age. Similarly, if we have some shells also in the same layer, we can date the shells by carbon-14 dating. However, if the age is more than 50,000 years, carbon-14 dating is not going to work. So in such cases, again, we fall back to the luminescence dating technique also. But normally if we are getting pottery, we know in a particular layer, if we are getting pottery, we know that this pottery is not that much old. Potteries are made only like 5,000, 6,000 years ago only. So whatever is coming, they are only 5,000, 6,000 years old, and we can date it either by the luminescence or the carbon-14 dating, or the charcoal. Charcoal also can be dated by the carbon-14 dating. Coins, obviously coins are the metal coins. Normally techniques are not there, direct techniques are not available which can date the coins, but we can date the sediments of the layer from where they are coming. Another important feature we generally observe in the field is we find layer of the potteries or the layer of the some like archaeological tools as a single layer, is in a very thin single layer. So we call it most of the time this is like a lag deposit. Lag deposit means these materials were somewhere on the top earlier, in layer distributed in upper layer like this. Then the sediment eroded away, whatever material was there, they are coming to single surface, after which next layer of sedimentation happened, and all these are appearing as a single layer. That means this is a lag deposit. This is not associated with this particular means all the tools maybe of the or pottery could be of same age or could be different age also, because they are the lag deposit. So generally in such cases we can date the sediment below it, but the sediment below it can be some of the times be quite old as compared to these tools. So these potteries, similarly with the tools, the sediment below can be much older as compared to the deposited tools. Similarly, the sediment on the top layer or on the layer on top of these tools may be younger to it, quite younger to it. So we have to we have to date both the layers, or if pottery is there, pottery we can date directly at times, but there will be some like inaccuracies because we are not getting the proper sample for the dating in such a case. Okay. Similarly, we can date the tool itself directly in some cases. I will tell how we can date the tools. Okay. Another material which we can date, obviously, we can date whatever boulders which are associated there. Some small boulders or pebbles which are there, we can date those pebbles layers. Sediment, obviously we can date. If charcoal is less than 50 kilo, if the layer age is less than 50 kilo year, we will be able to date with the charcoal. Or sometimes we also find the eggshells, ostrich eggshell or some other eggshells also. Those eggshells can be dating using carbon 14 dating if they are younger than 50 kilo a year. So these are some of the things which these are some of the datable material which we can use using luminescence. We can date the sediment, we can date the tools themselves, we can date the potteries, or like clay minerals we can date the coarse grain minerals. So also if some boulders are present, we can date those boulders also. So in case of sediment sampling, what we do, we generally have a sampling pipe which has a cap on the top. We open the cap and hammer the pipe into the section. Now, if you see some geological section like this, which has layer of different thicknesses, now can you take a moment and figure out which is the best way of sampling in such cases? I already told you that the sampling pipe has sampling pipe is a diameter is 5 centimeter, while the range of gamma is 30 centimeter. So basically, if I am saying my gamma range should be 30 centimeter, that means my pipe or my gamma, whatever radioactivity I am getting in this pipe where I am hammering pipe, sampling site, that should be covered up to 30 centimeters. So it should be enclosed within 30 centimeters. So if some sample is coming, say from the top, we have to correct for the gamma dose. Similarly, we should never hammer the pipe if some boundary is there between the two layers. We will always try to take sample from the center and try to take the measurement of the thickness of the layer and then correct for the gamma if needed afterwards. If the layer is very thin, we should avoid sampling such layers. We should also avoid sampling from the edge of the sedimentary section. So these are the important points while sampling for like sediment sampling using a pipe. We do it normally. So the best sample is this, where the 30 centimeter surrounding is clear. However, in most of the cases, we don't find this ideal situation. In such cases, we take the width of the sediment layer and then later on correct for the gamma dose, and also take some sample from the top and bottom so that we can measure the radioactivity of the top and bottom and accordingly correct for gamma dose in this sampling part. Okay, so this is how we go for the sediment sampling. In case of sediment sampling, precaution should be taken that we should select samples which we expect well bleached. We should, if it's a aeolian sample, it's our best sample. If it's like normally fluvial sample, we should try to avoid the flood deposits. We should try to see the sample which is well sorted, which we expect that it should have seen enough sunlight such that the luminescence signal should have resetted before the burial. We should avoid the places where animal burrows or the root cast, these kind of, or carbonate nodules are there, or cracks are visible in the soil. These will create problem during the analysis, because sometimes these activities, what they are doing, they are mixing the top and the bottom layer, so you will not get the good results afterwards. So we should try to take sample where such activities are not present. We should completely try to avoid, because precaution is always better than cure later. So try to avoid such sampling site where these activities are seen. After the samples collection, sample should not see light. It should be light tight. We should tightly pack it like in the metal pipe, or we should wrap it with the aluminum foil, multiple layers of aluminum foil, or the black polythene, thick black polythene, such that it doesn't see any sunlight after it is sampled. Otherwise, again, it will lead to loss of luminescence signal, and we will not be able to figure out in the lab what happened. Now, as I said, I will give the dating analogy. I said that this volume corresponds to the dose, this rate, volume rate, or the drop rate corresponds to the dose rate. So we can estimate the age simply dividing dose by dose rate. However, we should worry about the sediment mixing or bioturbation, because that mixing can change over volume. Or we should also be worried about leaking. We have a issue called anomalous fading in case of feldspar. So whenever we date the feldspar, we measure the fading rate, and then we correct for it. So we are aware that this is happening, so we can correct for it. But sometimes it may happen that for new samples, we don't know, like for some new minerals, fading is there and we didn't measure it. In such cases, we will end up in the problem. Okay, so this thing should be taken into account. As I said, partially bleaching means at T equal to 0, my beaker is not empty. That means some signal still remaining. It is not fully bleached. That may create some problem. Again, if my measuring instrument, either my instruments like my readers are not working well, or my radioactivity measuring instruments are not working well, or my dating procedure which I am using is not properly followed or not thoughtfully followed, then also we can end up in the wrong age. So we should be very careful in all these factors. At each step, we have to be very careful for estimating the age. Now coming to the sample preparation. So for the sample preparation, what we do, you can see the pipe in the background. So when we sampled, we know that the external outer layer is exposed to sunlight. This will come in this part. And also when we take out the sample, we know this outer layer could be exposed to sunlight. So what we do, we first of all remove these external 3 centimeter part from the top and the bottom of the pipe. We use this, we don't throw away these samples. We use it for the dose rate measurement purposes. Another important aspect is the dose measurement. So we use, for that purpose, we need a sample which is not exposed to the sunlight. So we use the center portion. And whenever one thing to be noted, whenever we hammer the pipe, we should hammer pipe completely, so that after we take out pipe, the sample is not shaking inside, so that these portion don't mix in with the center portion. Otherwise, this bleached portion will mix with the unbleached portion, and it will result in the error in our age estimate. So we use this part, center part, for dose measurement. We separate this part. We do chemical processing of this part, do HCl, H2O treatment for removing the carbonate, organic matter, and use HF for removing the alpha skin, and then separate the quartz and feldspar in the magnetic separator and measure the dose as I told you that we measure the luminescence signal, give the incremental beta dose, and then interpolate on the calibration curve to estimate the dose. Similarly, here we measure uranium thorium concentration and then measure the dose rate and estimate the age simply by dividing dose by dose rate. In case of the pottery sample, now the pottery sample is generally say 1 centimeter thick, okay, like 1 centimeter thick. Now we know that the top and the bottom portion of pottery may get exposed. So what we do, we remove the 2 millimeter outer skin of the pottery from both the sides and use the central portion of the pottery. Normally, since pottery is made with the clay, so we use fine grain dating for it, and a part of the pottery is broken and used for dose uranium thorium estimation. But as I told you, gamma is coming from the 30 centimeter surrounding soil, so we have to collect the surrounding soil also for estimating the gamma radiation dose rate from the surrounding soil. So we do have to, like in this case, we measure the radioactivity of the pottery also and the sediment also, and then estimate the dose rate, okay, for this portion. So this is how we prepare the pottery sample. Obviously, the actual process is much more involved. If somebody get a chance to come to lab and work on these TL dating techniques, I will show you how this can be done. Another sample I told you is rock sample. We can date the rock sample. So in case of rock sample, we can have a exposure dating also and the burial dating also. Exposure means if a rock is exposed to sunlight, what will happen? The top surface of the rock is bleached by the sunlight. So that means when this rock get buried, this top portion will have some dose information which is related to the age of the burial. However, another technique is there, which is rock exposure dating. Rock exposure means it is not buried. It is initially it was buried, then it comes to sunlight and get exposed to the sun. So what is happening? We know that light decays inside the material as a Beer-Lambert law. It decays exponentially. So here the intensity is highest. As it goes down, the light decays slowly. So what will happen? The signal at the surface immediately goes to zero, but inside the surface, it follows a sigmoidal form. So if we measure the signal as a function of depth, we get a signal like this. And when we fit a curve on this, so what will happen? If it is exposed to say 1 minute, the curve will look like something like this. If 1 hour, curve will look like this. If it is exposed to say 10,000 years, the curve will look like something like this. So when we fit the curve on this, we will be able to know what is the age of the sample using these equations. I will not go into the details. Okay, so using these equations, when we fit the curve, we will be able to tell how long the sample is exposed to sunlight. Now for burial dating, I said that this exposed surface again gets buried. In that case, what will happen? The initial signal is not zero. Initial signal is starting somewhere some non-zero value. So that non-zero value can be used to estimate the age of the last burial. Okay, this much signal is there. That means we can use this signal for dose estimation, and this dose corresponds to when the sample got last buried. So we can do in a rock sample, we can do both the burial dating also and the rock exposure dating. In the lab, how we do it? We take a rock, we take out a core out of this from the rock using this industrial table drill we have in our lab. Then we slice make very thin slices of this sample in our precision thin saw, and then measure the luminescence signal as a function of depth, and it shows like initially it is zero, then it starts increasing. So we fit the curve in this, and we will be able to tell the age, what is the age of the sample, or we measure the initial non-zero signal that tell us the last burial age of the sample. So this is how it is done, and it can be applied for the dating of the Paleolithic tools which you are having, stone buildings. Okay, in olden times, sometimes people used to make buildings with the stones. we can use this technique for stone buildings, exposure dating or the burial dating also. So like river boulders which are there, they undergo multiple cycles of burial and exposure. Using this technique, we get multiple burial and exposure. In such cases, what will happen, we get a staircases of burial and exposure events, and we can date each and we can estimate the age of each sample. So basically, for luminescence can be used for geology and archaeology, and we can date potteries or human evolution, lithic tools or sediments associated, and predict how the modern humans have evolved. In geology, we can date the movement of the glaciers, like we can date the frontal moraines, lateral moraines. We can tell when the glacier was there at that time. We can predict the motion of the desert, how the desert is evolving, how the sand dunes are moving. We can predict that. In the river sediment, we can date the river sediments and understand the fluvial processes, the flooding events, when the flooding event has happened in the past. We can predict the nature, how the climate has changed and how it has affected the river systems. Similarly, we can use that river terraces for dating the tectonic activities. We can see how the upliftment is going in mountains like in Himalayas. So these kind of studies can be targeted. Then we can date the tsunami events, and as I told you, the luminescence age ring is very wide. It varies from few years to right now, say 500,000 years. The youngest sample dated in our lab is around 6 years. The oldest sample which is dated in our lab is around 0.4 kilo year, 0.4 million years. Okay, so this is the range which we have worked so far. Also, like if there is some lightning event, we can date the material which is there, melted material which is created due to heating from lightning, fulgurites. We have dated the termites, or we are trying to understand how the mountains are evolving. There is a new technique called thermochronology. We can estimate at what rate the mountains are uplifting. So these are the techniques which can be used for archaeology and geology. I think I will not go into the details now. And finally, I thank all of you